Alright, so moving on, we're actually going to try, after having spent the last couple of examples making graphs given the equations, trying to actually go backwards now. Now that you're given a graph, try and go back and create what the original equation was. So it says here to determine two equations, one sine and one cosine, which model this graph. Now you might be wondering, well, how can I create a sine and a cosine graph a sine and cosine equation for the same graph? Isn't there only one equation? That's actually not the case. Because we have a pattern that repeats forever, you can actually create infinitely many equations for this that work. Okay, so it's just a matter of how you want to create them. So I'll show you how that works, but first what we're going to do is, just like we did with the equations, we're going to try and get all the main features from the graph. So i.e. what's the axis, what's the amplitude, what's the period, and so on and so forth. If we have all that information, we'll have enough to actually start creating the equations. So let's take a look at this graph here and see if we can figure out the axis. So what you're going to want to notice here, again, you may be able to read the axis nicely from the graph, but in case you can't, notice here that the maximum is at -1, and our minimum is at -9. So remember, the axis is halfway between the max and the minimum, so -1 plus -9 divided by 2, which winds up giving us y equals -5. Okay, so once we have that in mind, now we can actually work forward and try and find the rest. So let me just draw the axis in here at -5, just so you have the nice little visual. Okay, so now let's see if we can figure out our amplitude. So if our axis is at y equals -5 and our maximum value is at -1, that's a distance of 4. So we get our amplitude there. Okay, the other thing you can do, again, you're just subtracting the maximum value, taking the maximum value, subtracting the axis, and you get that distance of 4. So however you want to go about doing it, we have that information. And then our period, again, let's just do a check. We are in 3M, so it should be 360 degrees. Let's just double check. So let's just say we start the cycle here at -20 degrees. It starts to repeat itself at 340 degrees. So 340 minus -20, yeah, that's a distance of 360 degrees, which is good, because otherwise we'd be in 3U. Okay, so with all that information now, we're actually going to try and create a graph. Okay, so when you're creating an equation, again, remember that some of the key parts of the equation come from knowing the axis and the amplitudes. Remember, the amplitude would give you the A value, not whether it's positive or negative, or whether it's a reflection, but it gives you the actual value there. And the vertical shift comes from the axis. So you notice that we haven't even mentioned whether we're doing a sine or a cosine graph yet, and that's because we have the option. So remember that if we have an amplitude of 4, that 4 is going to be that first coefficient there. Now, it might be negative if we decide we have something that's reflected, but we'll deal with that later. Okay? We don't know if we have sine or cosine yet, but let's just leave that for now. We know our axis is going to be -5, so at the end of the equation, we're going to have -5. Okay? The only thing you have to decide here is, are we going to have a sine or a cos? Okay? We don't know what the phase shift is going to be, so it's going to be x plus or minus something. We don't know if there's going to be reflection. That's still a lot we have to work out, but again, we have options. We can go whichever direction we want. Okay, so what we need to figure out now is whether we have a reflection, whether we are doing sine or cosine, or whether we have a phase shift. So let's take it piece by piece, and let's just decide we want to do a sine graph. So I'm going to make that decision that we're going to find a sine graph. Okay, so then you might be asking yourself, okay, it's a sine graph. Do I want it to be a reflected sine graph or not reflected sine graph? And again, we have the choice. We can do as many of these equations as we want. So let's just say we want to keep it simple, and I don't want a reflected sine graph. So I want my equation to be +4 sine x minus or plus something minus 5. We need to figure out that phase shift. Now, we have to ask ourselves, okay, if we're going to do a positive sine graph, so i.e. a sine graph that has not been reflected, what's that going to look like? Okay, so it now comes back to knowing what the original parent function for sine x looks like. So this is a sine graph that has not been reflected, and you'll notice that the cycle starts on its axis and then goes up from there. So what we're looking for on our graph is a spot where the graph is on its axis moving up. And if you look here, there's actually 2 spots where that happens. Okay, let me just clear off this graph here. So where are we on the axis and then going up? So right here, the graph is on its axis, then moving up from there. And it also happens here as well. Okay, so we actually have two different choices. Let's say I use this one right here. If I use this point right here, well, what's the phase shift? Well, again, on the original parent function, the cycle starts at 0 degrees. Now this cycle is starting at negative 20 degrees, so my phase shift is left 20 degrees. And if my phase shift is left 20 degrees, I have x plus 20 degrees in the equation. Okay, and this is a perfectly valid equation for this graph. But let's say I wanted to use this one instead. This would be a phase shift of right 340 degrees. And this equation would work just as well. I could have a possibility here of y equals positive 4 sine of x minus 340 degrees minus 5. And this would be the exact same graph as this one. This would both be these would both be acceptable. Okay, so let's say I want to create a sine curve with no reflection. Well, again, this particular one here has left 20, but we can also do right 340 degrees. Okay, and there's our equation. So, okay, so again, we just arbitrarily decided that we wanted to do a sine curve that had no reflection. Okay, well, let's say we want to do a sine curve that does have a reflection. I know it says only do one sine, one cosine. Let's just take it a little bit further. Let's say we want to do a sine curve that has a reflection. Well, again, the only difference is if you look at a sine curve that's been reflected, it still starts on its axis at the cycle, but then it goes down from there. So in our graph, we look for a spot where we're on the axis and then going downwards. And you'll see that happens right here. Okay, the graph is on its axis and then moving downwards. So this would be a phase shift, again, from 0 to positive 160 of right 160 degrees. So in that case, if we know our phase shift is right 160 degrees, the only thing that changes, you notice that the amplitude is still the same. The amplitude is still 4. The axis doesn't change. All that's changed is now my phase shift is different, so it's right 160 degrees. And now, because this had a reflection built in, I have to make sure that I have a negative attached to that a value. Okay, and again, this graph will also look identical to the two we've already created. Okay, so now we've created actually two sine graphs that were not reflected, one sine graph that is reflected. Now let's look at a cosine curve. Okay, so for a cosine curve, again, you have to know that cos x starts its cycle at its maximum value. So where on here is the graph at its maximum value? Well, we can take a look and see it happens right here at 70 degrees. So this is a phase shift right 70 degrees. And what's our equation going to look like? Well, it's not reflected, so the a value will be positive. So it'll be positive 4 cosine x minus 70 degrees for our phase shift, and again, minus 5. So again, only thing that's changing is now we have cosine, it's positive because it's not reflected, and we have a new phase shift. If we want a reflected cosine curve, notice that's not going to start at its maximum, it'll start at its minimum value. Well, where are we at the minimum value over here? Well, that's right down here. And this will be at, looks like 250 degrees. So, phase shift of right 250, which means we have x minus 250 inside the bracket, and again, now our a value is negative because it's been reflected. All of these equations will produce the exact same graph. Okay, and I'll show you. I'll just prove it to you using Desmos. Okay, so here are all our possible equations typed in. You can see there's the first one I came up with, and all of a sudden a second one, same graph, same graph, same graph, and same graph. Okay, so all of these are perfectly equivalent answers. It'll all be perfectly valid on a test or quiz. Okay, so with that in mind, there's a lot that will happen there. I would like you to try one on your own. So here's another graph. I'd like you to, again, find all the key information, axis, amplitude, period, and put that information together and try and create. Now it says only, again, one sine and one cosine curve, but let's push that a little bit further and then try to do one of each. So try a sine curve that has no reflection, one with a reflection, and two cosine curves, one with reflection and one without a reflection. Okay, so give that a try. See how it goes, and push play when you're ready to go through it together. Okay, so just check your values here. The axis is at y equals 3. Period is still 360 degrees. Our amplitude is 5 because our max is at 8. Axis is at 3, so that's a distance of 5. So again, the amplitude and the axis will both start and end your equation no matter which one you're doing, whether it's sine, cosine, positive or negative. The only difference is if it's going to be reflected, you have to make sure that the a value is negative. So again, once you have that, then you're deciding whether you want sine or cosine, whether or not you can have a reflection or no reflection. So what you're looking for is, again, to start at the same spot that the parent function would if it was reflected or not reflected. So let's say you're looking for a sine graph that is not reflected. That starts on its axis, then going up from there. So that would be at this point right here in red. So if you, let's say you choose that one, this x value looks like it's 115 degrees. Yeah, 115 degrees. So it means it's a shift right 115. So you have y equals 5 sine x minus 115 degrees plus 3. Okay? If you want a sine graph that was reflected to be on the axis but then going down from there, like you have over here in orange. So that looks to be at 295 degrees. So again, phase shift is right 295, and you change your equation accordingly. And again, because it's been reflected, please make sure that you have the a value being negative. Okay, for the cosine curves, if it's not reflected, it starts at its maximum like it does at the black point right here, which is 205 degrees to the right as a phase shift. Okay, and if you do have a reflected cosine curve, will start at its minimum like this point does over here at 25 degrees. Okay, it actually looks like it happens again over here at 385, which makes sense because the period of 360 degrees. This one's a little bit easier to use though, so we'll use right 25 for our phase shift, and again, the a value is now negative. Okay, and again, if you could continue this graph on for another cycle, you could pick different values for the phase shift and create more equations that were equivalent, but there's no need here. We already have 4 different equations that will work. Okay, so hopefully that makes sense. Again, it takes lots of practice, but eventually once you've done a few, these can go relatively quickly. Okay, let's change things up a little bit and bring back some function notation from previous units. So given f of x equals cos x and g of x equals negative 5 f bracket x plus 45 degrees minus 9, A asks for the equation of g of x. Now, again, it just seems like there's a lot going on here, but remember, this is all just the function notation stuff we've been doing since the start of the semester. So if g of x is negative 5 f at x plus 45 degrees minus 9, what makes this tricky is that f at x plus 45. But remember, f of x plus 45 is just taking the function f and replacing x with x plus 45 degrees. So if you're thinking about this one, well, f of x plus 45 degrees, if f of x is just cos x, is going to be equal to cos of x plus 45 degrees. Okay, and once you have that, then you know you can replace that entire part of the equation with this, and it becomes a little bit easier to work with. Because now all of a sudden, g of x, ooh, that's a bad g, g of x is equal to negative 5, and f of x plus 45 is just this cosine portion right here, negative 5 cos x plus 45 degrees, okay, and then again, minus 9. So just applying function notation to get my transformed cosine graph. Okay, once it's in this form, it looks a bit more familiar, right? There's a lot of information you can get about this now. You can get the amplitude, the mapping rule, the phase shift, the axis, and all that kind of stuff. So now that we have this, part B asks you to determine 2 different but equivalent equations for g of x. Okay, now we already now know that there's multiple different equations that can represent one graph, but the best way to sort of get the other ones is to do it graphically. So what you should do to help you answer B is to create a graph of g of x using the grid provided. And once you have that information, again, you can then start choosing if you want a sine graph, you can pick a starting point on the axis. If you want another cosine graph, you can start at the maximum and then go from there. Okay, but what you're going to need to do for this one is actually make a sketch. So I'm going to have you do that, and when that's finished, move on to part 3, and we'll go through the rest of the problem there. But make a sketch of this on the graph provided. Okay, that's it for now. Cheers.